Welcome to all. This is Dr. Vigneshwar Meka, Assistant Professor of Geography, Government Degree College for Women's, Autonomous. In this video, we are going to focus on the insolation influencing factors, part 2. The part 1 session, we have covered the following points: the introduction to insolation, sources of the solar energy, solar radiation, solar constant, and factors influencing distribution of insolation. And in this session, we will focus on the atmospheric depletion of solar radiation. So as a part of the session 1, or the insolation influencing factors part 1, we focus on the introduction, sources of solar radiation, energy, and the definition of the insolation, and the factor, the solar constant, then the factors influencing insolation. As a part of it, we focused on the various factors such as the angle of incidence, duration of the day, solar constant, distance between the sun and earth, and transparency of the atmosphere. So these slides, the pictures, and discloses you about the angle of distance, and this is about, this table discloses you about the duration of the day, and this discloses you about the duration of the day at equinoxes, during the equinoxes, and the third is the solar constant, and the fourth factor is the distance between the sun and earth, and fifth is the transparency of the atmosphere. Due to the transparency of the atmosphere, the influence is, the fact insolation is influenced, and as a result of it, the depletion is taking place. So in the present session, we will focus on the atmospheric depletion of solar radiation or solar insolation. The loss of solar energy in passing through the atmospheric layers is called the atmospheric depletion. It depicts how solar radiation has to traverse thick and denser layers of the atmosphere in reaching the surface of the earth. The longer the path traversed, the greater amount of the solar radiant energy depleted. The various processes whereby heat energy is lost through the temperature are presented in the following points. They are: 1. Scattering, 2. Diffusion, 3. Absorption, and 4. Reflection. Now, we will discuss the processes resulting in the atmospheric depletion of solar radiation. Firstly, we will look into scattering. The atmosphere is composed of the molecules of air, water, vapor, and dust particles. These molecules scatter the shorter ultraviolet waves in different directions. This process in meteorological parlance is known as scattering or scatter. The solar rays consisting of light and heat waves of different wavelengths. When ultraviolet rays pass through such molecules as have diameters shorter than their wavelengths, the blue and violet color spectrums get scattered. But the red color spectrum with the larger wavelengths managed to reach the surface of the Earth. Thus, when we look at the sky away from the direct rays of the sun, we see more of blue light which was more readily scattered. At sunrise and sunset, the oblique rays have to pass through the longest path of the atmosphere, hence all the color spectrums except the red and orange are scattered. It is only the red and orange colors that reach our naked eyes. This accounts for the reddish of the sky during the twilight hours. The figures on the screen discloses you about the scattering of blue and red colors. The color spectrums which are expected, the red and orange, are due to the scattering. The second process of atmospheric depletion is the diffusion. When the diameter of the particles is larger than the wavelength of the incident beam of light, true scattering does not occur, and effect of the particles is of the nature of diffuse reflection or diffusion. It is effective for all wavelengths. Since the process of diffusion is non-selective, component colors of the incident light do not get separated. That is why the light reflected from a cloud when the sun is behind the observer is pure white. The sun, for the same reason, appears white when seen through a fog composed of water droplets. It is principally due to the fusion of light in all possible directions by the dust particles present in the air, and we have sufficient working light before the sunrise and after the sunset. This diffuse light is called the twilight. The astronomical and civil twilights last till the sun as sun below the horizon 18 degrees and 6 degrees respectively. The twilights are of longer duration in high latitudes than in low latitudes. It is of interest to note that it is mainly due to diffuse reflection that there is light in the rooms and under the trees. Thus, solar radiation suffers loss through diffuse reflection by larger particles such as cloud droplets, which occur in greater quantities at low latitudes in the atmosphere. There is difference in the effects of small particles and cloud particles that are relatively larger. The molecules or small particles scatter a larger percentage of light of shorter wavelengths, causing the direct beam to be richer in red rays and the scatter light to be richer in blue rays than the incident light. On the contrary, the larger particles in a cloud are incapable of producing any change in the relative intensities of the different wavelengths. When a cloud appears reddish in color in the atmosphere, it should not be taken to be the result of a selective scattering effect produced by the cloud particles themselves. It is an account of the loss of blue light by scattering from the beam illuminating the cloud. The picture on the screen discloses you about the diffusion by the clouds and also by the particles that present in the atmosphere. The figure on the screen discloses you the processes of scattering, the process of reflection, transmission, refraction. Besides them, it also refers to the absorption. Absorption has been defined as the process in which the incident radiation is retained by a substance and is reversely converted to some other form of energy. There is a certain amount of radiant energy lost by the process of absorption in the atmosphere. It may be pointed out that gases do not play a very significant role. Since they are selective observers, their capacity to absorb solar radiation differs for different wavelengths. When a gas molecule absorbs light waves, this energy is transformed into internal molecular motion, which causes a rise in temperature. Nitrogen is a very poor observer of incoming solar radiation or insolation. Oxygen and ozone that are present in the atmosphere are said to be the good observers of solar radiation shorter than 0.29 micrometers. At high altitudes, oxygen absorbs most of the ultraviolet rays. In that stratosphere, the ozone removes ultraviolet radiation of relatively longer wavelengths. The most important and efficient observer of ultraviolet radiation is water vapor, which along with oxygen and ozone absorbs roughly 15% of the total solar radiation within the atmosphere. In addition, carbon dioxide gas, which is present in the atmosphere in very small quantity up to the great heights, is an efficient observer of incoming solar radiation that comes in the wavelengths of about 15 microns. In the direct absorption of incoming solar radiation, the water vapor present in the lowermost layer of the atmosphere plays the most significant part. In the electromagnetic spectrums, a larger percentage is comprised of the infrared waves. According to Kendrieu, about 43% of the incoming solar radiation is received through these longer infrared waves. A larger percentage of these longer waves is directly absorbed by water vapor. It may be mentioned that after the gases absorb incoming solar radiation, they become heated by conversion of radiant energy into heat. Thereafter, these absorbing gases start radiating the converted heat as long wave radiation. The cloud drops in the atmosphere as well as the dust particles have little contribution to make in the absorption of incoming solar radiation. So these are important for the purposes of scattering and diffusion reflection. Thus, it is clear that the loss of incoming solar radiation in the atmosphere is in direct proportion to the amount of water vapor present. Since water vapor is mostly transparent to the shorter wave ultraviolet rays and opaque to the larger infrared rays, it acts as a screen to long wave radiation. The shorter ultraviolet rays pass through this gas clearly, but longer waves of the incoming solar radiation are partly absorbed. Similarly, water vapor is an effective absorber of long wave terrestrial radiation. In fact, water vapor is most effective regulator of surface temperature of the Earth. This effect of the atmosphere is known as the greenhouse effect. In a greenhouse, the glass walls or glass roofs allow the short-wave solar radiation to pass through them, where it is absorbed by the ground and converted into heat. But the long-wave terrestrial radiation is not allowed to escape the roof and the walls of the greenhouse. Thus, the heat inside the greenhouse is maintained at a certain level. The next process of atmospheric depletion is reflection. A part of the incident radiation falling on any surface is reflected back into the space. It is called the reflection of the light. Thus, a certain amount of energy is lost and it does not play any role in heating the atmosphere. The reflectivity of a substance, usually expressed as a percentage of the incident radiation reflected, is known as its albedo or reflection coefficient. It differs from place to place as well as from time to time in the same locality. It depends upon the amount of cloudiness and atmospheric impurities, the obliquity of the sun rays, and the nature of the surface. The albedo for the Earth as a whole, also known as the planetary albedo, and which is 35% or 35 units. The albedo of the various surfaces on the Earth varies. The albedo of the fresh snow is 80 to 85%, old snow 50 to 60%, sand 20 to 30%, grass 20 to 25%, dry air 15 to 20%, wet air 10%. And the forest albedo is 5 to 10%, Water, that is sun near horizon, 50 to 80%. Water near sun near zenith is 3 to 5%. Thick clouds, 70 to 80%. Thin cloud, 25 to 50%. And earth as well as the atmosphere, 35%. It is to be noted that clouds play the most important role in reflecting the incoming solar radiation back to the space. Another characteristic feature of the planetary albedo is the fact that the Earth's land sea surface accounts for only 4% of the total of 35%. The albedo of water surface depends upon the altitude of the sun. When the altitude of the sun is 47 degrees, the albedo varies from 3 to 5%. On the other hand, when the sun is near the horizon, that is at about 5 degrees, the albedo is found between 50 to 80%. So far, we dealt with introduction to insolation, sources of solar energy, solar radiation, solar constant, factors influencing the distribution of insolation, and atmospheric depletion of solar radiation.